The very first flight that was powered and controlled took off from the Kitty Hawk Beach in North Carolina in 1903. I'm sure many of you have seen this picture, but look closely. You're going to see the enthusiasm and the excitement of the observer first. And if you look even closer, you'll see the same for the pilot, who's holding sticks and using hip movement in order to command the speed, altitude, and the orientation of the aircraft. Not too long, but just 60 years later, that pilot is now endowed with technology and is only limited by the physics of his environment. The aircraft literally melts as it goes through the air, and it took only 60 years. One thing that didn't change was the pilot, still holding the sticks, using the pedals to change the speed, altitude, and orientation of the aircraft. Now, this is what people associate with drones most of the time. It's a full-size aircraft. It's a remarkable picture because when you look at the aircraft, you see there's a little bump in the front. You would feel like it's a cockpit. A person goes sit in there, except there's no windows. That's why it's so remarkable. In fact, the person doesn't sit in there. The person sits tens of thousands of miles away to pilot this aircraft. However, the control mode is very similar. The pilot has sticks, and that can change the speed, orientation, and the altitude of the aircraft. Fast forward a couple decades later, especially in Ukraine, taught us these small FPV drones and their value in defense. And one of these drones fits in a backpack, you take it out, you lift it up, and you know what? You use the sticks to fly it so that you can control speed, altitude, and orientation of the aircraft. In fact, most of our UAV categorization starts out with this human pilot first approach. When you look at the UAV categorization, we categorize them from group 1 through 5. Group 1 is the aircraft that's the smallest, typically flies at less than 100 feet and less than 100 knots, meaning about less than 100 miles an hour of speed. As the groups increase, the altitude, the speed, and the weight of the aircraft increase all at the same time. And typically, these aircraft are still, today, piloted with the sticks, except just remotely, depending on the situation. So now, here's an aircraft that we've been working on. This aircraft is fully autonomous, and when I say it, I mean it genuinely. It has a supercomputer on board. It has the AI and the autonomy to perceive its environment. By that, I mean it can detect obstacles, it can know where it is, it can understand the context within its environment, it can make decisions that are mission critical and do them very, very rapidly. Here it's given a bunch of waypoints. It is operating in a place that it's never seen before. It just wakes up in this frozen land, and it's able to go to its first waypoint by just tracking where it started. It sees a line of trees. It knows that it shouldn't be hitting that, so it gains altitude. And it discovers a frozen lake, a frozen river. And at that point, it understands that it could just lower the altitude just a little bit and reach its next waypoint. Its ability to understand where it is, understand its surroundings, without using any external aids, means that it can operate in a denied environment. It can operate when communications are denied, when GPS is denied. It can make decisions, it can understand its environment using just the onboard compute that it has. The low altitude enables it to operate not just in denied, but in contested environments. By flying at low altitude at a high speed, this vehicle literally flies under the radar. So now, when you look at this categorization, expanding out, we envision aircraft that fly less than 100 feet in altitude, like Group 1, but not less than 100 knots, but more than 100 knots. In fact, up to 200 knots, 200 miles an hour speed. So those would be the kind of aircraft that we would make it so that it would be fast, agile, and reach extreme speeds. We also think of aircraft that are not just kind of growing in size, but actually getting miniaturized and becoming embedded and ambient in the environment. This is a new kind of approach that takes autonomy first, as opposed to the pilot, and envisions the entire UAV ecosystem around this autonomy approach. So let's take a look at these groups. The first group will be the fast and the agile. So I'm going to describe a set of vehicles that can fly less than 100 feet in altitude, but more than 100 knots, in fact, up to 200 knots. And so these will be the vehicles that can come out of a backpack as like the usual Group 1 aircraft, but that can fly fast and low altitude to go in contested environments. Here we've built the very first Group X UAV. This is an aircraft that can fold and fit in a backpack that can fly 200 miles an hour on electric propulsion. Now, I know that you've heard from many people that they can actually exceed these speeds, go up to 300, maybe 400 miles an hour. Now, unfortunately, those are not very mission relevant because they'll run out of battery in 3 minutes and they'll go maybe a few miles. This kind of aircraft can travel 50 kilometers. With extended wings, it can go up to 100 kilometers and it can stay in the air tens of minutes. But most importantly, what it does is that underneath the hood, it carries a supercomputer. And that supercomputer, it enables to fly at the low altitudes while avoiding obstacles and while understanding where it is and make these critical decisions. In fact, I think its most important differentiator at Group X is the computer that it carries as opposed to the speeds that it can reach. So you would say that, okay, that was exciting. So we can go 200 miles an hour and a mission-relevant capability with autonomy, building the vehicles with autonomy from the ground up. So why stop at 200 knots? So that's where you can typically push electric propulsion to mission-relevant environments, electric propulsion to speeds. We don't have to stop there. If you have other kinds of propulsion, for example, if you have jet motors that can fit in your palm, you can actually go up to 400 knots. This is an aircraft that we've been playing with. It's about this large, and it can do 400 miles an hour. And it will fly at that speed tens of minutes, so it can cover a long distance. So then Group Y aircraft would be those that go under 100 feet, but up to 400 knots. Of course, you don't have to stop there either. You could go even faster under the radar. In fact, at MIT, we've been playing with rockets, rocket engines, that are steered by 3D printed jet vanes, 3D printed out of niobium. And that allows us to steer the jet so rapidly that we get a very agile vehicle, which we think we can take it all the way down to 30 feet altitude. And these are slow-burning rockets, so they could travel for tens of minutes, taking the vehicle almost to the speed of sound, and still have the same kind of intelligence that I just talked about. So then that would be a Group Z type of new kind of vehicles enabled by rocket propulsion, but most importantly, enabled by the computing and the AI that's on board. Another group of vehicles is what you get when you start scaling things down. I'll talk about this quickly. So the first group would be Group Alpha. These are the vehicles that, as opposed to fitting in your backpack, they would fit in your pocket. You would take it out and literally throw it in the air in order to deploy. It would take a few seconds just for them to deploy. Group Beta vehicles would be those that end up fitting, measure 1 inch in size, and end up fitting in a tray. And inch by inch in size, on a foot by foot tray, you would have 100 of them. You could put the tray on the floor to deploy them. Better yet, you can throw the tray in the air. And now you have 100 drones up in the air already deployed. 1,000 of them would fit in somebody's backpack. Group Gamma vehicles would be those that are indistinguishable from an insect, unless you're just a few feet apart. You don't deploy them anymore. They are ambient. You already have thousands of them in the environment that you're walking, and they can just step in when you want them to. Interestingly, we have the mechanics and the structures to build all of these aircraft. The reason why they don't exist is because we don't know yet how to put the AI and autonomy at such a small scale. At MIT, we've been also working on how can we get towards that direction. So we've been building chips that measure just a few millimeters, expand just a few 100 milliwatts of power, and they can do some amazing things at that scale. For example, in one demonstration, we've shown that they can know where they are, just using cameras and inertial measurement units. So in this example, the vehicle goes around, looks at the video, looks at the inertial measurement unit, and understands where it is with respect to its starting point. And it's almost as good as the ground truth, which we get from a motion capture system. We've also built chips that can do mapping, for instance, that can map the environment as they evolve. So as we think about AI and putting AI onto vehicles, either small or fast, you can project and see as AI gets better, where could this go? My prediction is that very first, AI will start to surpass human comprehension of speed. We can do this already, where we can fly drones fully autonomously that a skilled pilot looking at the video would not be able to comprehend in real time what just happened. As you push the technology further, next what's going to happen is that AI in drones will go beyond human comprehension of complexity. A typical operator today can really keep track of 10 assets at a time. Now imagine AI that could keep track of tens of thousands of friendly or foe assets, and that could understand the different relationships, and that could plan ahead for what to do within that context. A mission that could last just minutes would be so complicated that reviewing it, us as humans, could take a whole lifetime to understand what has happened in this mission. And as AI makes more and more progress, the next stage would be going beyond human comprehension of strategy. This would be when the AI is able to keep track of so many different contingencies, of friends and foes. When friends disappear from the screen, go down into a communication-denied environment, the AI could think about what the friend is thinking, what contingencies they may have, hence where they might reappear, hence they could change their plan. AI could think through different contingencies in order to trick the adversary in ways that would never occur to a human, even if we sat here and spent a whole lifetime to come up with a strategy to go and fight. This sounds maybe too sci-fi, but I would tell you that this is already happening in small domains, like chess, for example. There's no human beating chess today, and it feels like every time you play it, AI has one more strategy that humans will not be able to come up with the 1,000 years that we play chess. And it's a matter of time that that's going to get into more and more complicated environments. So what now? What now is that it's pretty clear to me that computing will change many industries. But I think that it's going to change defense and security the most. And we don't realize it right now, but the kinds of vehicles, kinds of systems that are in development right now is going to absolutely transform the security landscape throughout the globe. When we look back one day, I think we're going to see this impact of this intelligence in a box operating together with its friends in order to protect is a hugely valuable technology that changes everything. And one day we might think that its impact has been no different than the rifle or the battle tank or aviation itself. And we may value it that closely. And it's up to us to build it and use it wisely. And I hope that it'll help us protect democracy, liberty, and freedom throughout the world. Thank you so much.